talking about chapter 15. We're switching gears. Chapter 14's focus was kinetics. How fast chemical reactions are occurring. What's the rate of the reaction? What's the order? What's the activation energy? Now we're switching gears and we're looking at chemical equilibria. So now we're looking at what happens when the rates become equal to each other. So we're going to look at the concept of what dynamic equilibrium means, how we define the equilibrium constant K, the significance of it, how we write them, how we can rearrange them. We're going to hammer all that stuff out. How we deal with it if we have a gas and we're dealing with pressures instead of molar concentrations. Heterogeneous equilibriums. So if we have one phase, how do we deal with it? What do we do with it if we have multiple phases? So heterogeneous, we're going to have multiple phases there. How do we deal with multiple phase systems? And then how do we calculate these Ks? And there's an acronym that we use that's ICE, stands for initial change equilibrium. How do we apply that to systems? And then we can look at what the value of K is and predict, is the reaction under the current conditions, is it going to go progress forward as written, or is the reaction going to go in the reverse direction to reach equilibrium? That's important to understand. If you know some initial concentrations, what's going to happen? Is it at equilibrium, or what reaction is going to go on? So we can compare Q versus K to predict that. Then we're going to look at calculating equilibrium concentrations and look at exact solutions using mathematics, and sometimes we can make some approximations to solve the math. Now, and when I teach this topic in a course called Chemical Analysis, we'll set these up and we will do systems of equations that will involve 5 and 6 equations and 5 or 6 unknowns. To solve that, it's a 5th or 6th order polynomial. We solve them with a computer. We don't do matrix algebra. Nobody does. Not when you have something like Mathematica that can give you an exact solution in a matter of seconds. The most complex equation that we're going to solve is your old friend from high school, the quadratic equation. But we're going to have to solve some quadratic equations. Then the last part of the chapter is the influence on change. And that's covered by something called Le Chartier's principle. It looks at what happens when you change concentrations. How's an equilibrium shift? If it's got a gas, what happens when you change pressure and volumes? And then finally, what happens if we influence the temperature? Right down at the bottom, there are more suggested problems in this chapter than any other. At least a dozen problems, closer to 15 there. And the Mastering Chemistry assignment's a little bit longer. Chemical equilibrium is used in every chemistry class beyond Gen Chem. This is really an important one to get a strong grasp on. I mean, it goes into biochemistry and everything else. It just it does not go away. So what are some of the applications of chemical equilibrium, and why does it influence us so much? Why are we concerned about it? One example is to look at a biological system, look at the protein hemoglobin. Hemoglobin's abbreviated HB. Its job in the body is to transport oxygen that comes into the lungs and transport those to blood cells where the oxygen is exchanged for carbon dioxide, and the carbon dioxide that's been metabolized is carried back out to your lungs. It exchanges, comes out, we breathe out the O2, or breathe out the CO2, fresh O2 comes in. So what happens is that hemoglobin binds with the oxygen at the interface of the lungs, and it forms this oxygen-hemoglobin complex. And the fact that these arrows are pointing both ways means that it's a dynamic equilibrium. The reactions are simultaneously occurring in the forward direction and the reverse direction. And it depends on which one has the highest tendency. Would this hemoglobin rather be free, or would it rather be bound to the oxygen? Is going to depend on which side that equilibrium favors. It may not favor either side. It may be balanced. It occurs in different ways. So if we think about it, though, the concentrations of hemoglobin, O2, as well as bound hemoglobin are all related to each other, or interdependent on one another. So what happens is that there is an equilibrium established, and there is what's called the equilibrium constant that defines the mathematical relationship between those relative amounts or concentrations. And if there's a large value for K, that means that the products are the thing that's favored. And the opposite is true. If it's a small value for K, it means the reactants are the things that are favored in that particular equilibrium. But if we change the concentration of any one term in this system, so hemoglobin, oxygen, or the bound hemoglobin, what happens is it's going to force a response or a change to everything else. They're all interrelated or tied together. You change one component, the others have to do something to respond to that. So if we think about what's going on in the lungs, we breathe in air. The oxygen in the air at sea level is about 22%, okay, by mole ratio. So there's a fair amount of high concentration of gas there. And the fact that there's a high concentration of gas causes that oxygen to bound to the free hemoglobin at the surface of the interface in your lungs and make the bound hemoglobin. The equilibrium shifts in the forward direction to the right because there's a large amount of oxygen present in the system. So what happens is it transports the oxygen, it goes to the muscles, and in the muscles where there's a low concentration of O2, now the low concentration of O2, the oxygen decides, well, I would rather be free, so the equilibrium shifts back to the left, and now it releases more O2 to get more concentration of oxygen at the side of the muscles or whatever the cellular event that's needing that needs the oxygen. The equilibrium shifts back and towards the should be the opposite, right? The equilibrium shifts back in this direction, shifts to the left. Okay, so now the complex that's carrying the oxygen falls apart, and now the concentration of free O2 is going to go up in the system. It's the thing that's going to increase. And then this process is repeated over and over and over every time we take a breath and blood goes through our body and goes to our heart, pumps to our lungs, and then goes to the cells. Now, when hemoglobin is made by the body, it changes over time a little bit. So there's something called fetal hemoglobin, and that represents the hemoglobin that's present in a fetus. So what's happening in a fetus as it's developing, it's not breathing oxygen into its lungs yet. All right, so it's a little bit different than normal hemoglobin, and that equilibrium constant is a little bit different. So fetal hemoglobin's equilibrium constant is larger than that than the adult hemoglobin's constant. And the why is that fetal hemoglobin has to be more efficient at binding the O2. So if you've had some physiology or understand what's happening inside of a wound, if we think of the process, we've got hemoglobin binds to the oxygen inside of the placenta, and what happens is you have a transfer from the oxygen that's coming in from the mother to that of the fetus. So what happens is the hemoglobin from the fetus has to bind it more strongly. It has to transfer the oxygen that's coming in from the mother's artery. It has to transfer that across a membrane and go into the fetal artery. So the oxygen the hemoglobin that the fetus has to bind that oxygen and steal it from the mother's oxygen. For that to occur, it has to have a higher binding constant associated with it. All right, so if we start thinking about that process and what's going on in terms of the physiology, that chemistry starts to change as soon as a fetus is born. As soon as it starts to take its first breath, comes out of the womb, its hemoglobin starts to go through a process where it changes to become like adult hemoglobin. All right. Now, if it binds it too strongly, one of the problems is it doesn't release it out to the cells. And there's some blood diseases that are like that cause deficiencies in the mechanism in which hemoglobin should change and the fetal hemoglobin never matures to adult hemoglobin, and that's going to cause a problem in what happens to that child's health. Bart's disease is one of the things that happens. It's a one amino acid defect that doesn't correct with time, and it changes the efficiency in which hemoglobin is transported from the lungs throughout the cells, and it decreases the efficiency of the lung capacity in the hemoglobin by over 50%. In some cases, children with Bart's disease, majority of the children never make it above age 16. And right now, we don't have a replacement for it. So they can stay on oxygen, and they can live a life, but and if they, as long as they don't over-exhilarate themselves, where they need to get in a high demand of oxygen, most of them can live fine doing a non-stressful environment, but they're going to be limited on what they can do. Their sports are going to be something they can't do. It's just one of the defects that nature threw at us. All right. Now we look at the reaction dynamics and what's going on. When a reaction starts, the reactants are being consumed and products are being made. It's going in the forward direction. So that means the concentration of the reactants are going to be going down, and the concentration of the products that are being formed, its concentration is going to be going up. So as long as you have a decrease in the concentration of the reaction, we know the reaction's proceeding in the forward direction. Okay, but eventually it's going to reach some point where the products start to decompose and they start to remake some of the reactants. That's assuming the products are not taken away. The reaction's going to be running in the reverse direction a little bit. All right? So as we start to get more and more products made, the rate at which the reverse reaction occurs starts to become quicker. Well, initially you don't have any products, so it can't go backwards. But as you go further and further and make more on the product side of a reaction, now it can start going backwards. So processes, or when we say processes, chemical reactions that can proceed in both the forward and the reverse direction are said to be reversible. Okay? So that means you have a system where the reactants can go to the products, the forward arrow, or the products can decompose to form the reactants, reverse arrow. Not all systems are reversible. Okay? Sometimes reactions can only go one way, and then if it comes back in the reverse direction, it forms different products other than the reactants. So different systems respond differently. Most are reversible, however. All right. So here's kind of a graphic example. If we look at dinitrogen tetroxide, N2O4, it's a colorless gas. It can convert to, basically split in two to form two nitrogen dioxide, N2Os. All right, so our NO2s. And the NO2 has a brown color with it, associated with it. So if we started with only, as written here, with the products, so are the reactants. So start with this reactant, that'd be this case. Start with only this guy. So it's represented by the green color. What happens is it starts to go forward in the reaction, and as its concentration is going down, this concentration of the product, NO2, is starting to go up, and you'll see it's changing twice as fast. And why? Because there's two of those being created for every one of these being consumed. But at some point in time, whatever that time is, the system reaches a point where the forward rate equals the reverse rate, and the concentrations don't change. Okay, that's the point of equilibrium, where concentrations don't change with time as equilibrium. Now, if I went and looked at the other side of the reaction, now I'm going to start with the products. I'm going to start with this brown gas over here. All right, so I've got NO2 in there, and there's none of the product. If I just put that in a container by itself, what happens is it starts to decompose, the reaction goes backwards, and then the product is now formed, okay? So it again reaches a point where it's at equilibrium. So I could start with the product, and it's still going to run backwards until I get equilibrium. Or I could start with a mix of the gases. So if I started with a little bit of the reactant and a little bit of this product, in this case I've got more reactant, so the reaction proceeds in a forward direction. So with this one, what happens is it proceeds forward, forward. So is it going in the forward direction or reverse direction? Why? Why do you think it's reverse?
You're getting more into forward.
Which is a reactant in the way it's written. Exactly right. So this concentration is going up. So that means for that to occur, the reaction had to be going in this direction. All right. So it has to be running in the reverse direction. So to reach equilibrium in this system, even though I started with some of both, the balance is that some of this product has to decompose to make more of this reactant until it gets to the point where the concentrations are not changing. That's the point of equilibrium. Now, all of these things, it doesn't matter what you start with, whether you start with a mixture, whether you start with the reactants or start with the products, given time, the reaction is going to reach an equilibrium, a point where the reactants and the products don't change in concentrations. Now, how long is that time going to be? Well, that's a question for kinetics. Okay, so we have to separate what we did in the last chapter. Kinetics is about how fast this would occur. Now we're just concerned about what are the concentrations. Okay, so we're looking at it from a different standpoint. Now we want to know, what is this ratio of the concentrations? Are these concentrations going to be at the end? So when we look at this equilibrium that's going to occur, as the forward rate our reaction starts to slow down and the reverse reaction starts to accelerate, eventually at some point, and here's the key thing, the forward rate is going to equal the reverse rate. So the rate going forward and the rate going backwards, and we said rate was in molarity per second, if those rates equal to one another, there's no net change. And that's what's happening in chemical equilibrium. So we use the term dynamic equilibrium to represent the fact that if I change one thing in the system, everything else has to respond. That's what makes it dynamic. Okay, like in the hemoglobin, if I change the hemoglobin or the oxygen or the bound hemoglobin, if I change one of those sort of things, the whole system responds. That's the dynamic issue associated with it. But we say it's at equilibrium when the forward and reverse rates are equal to one another. So once the system has reached equilibrium, the concentrations remain constant at that point because the chemicals are being both consumed and produced at exactly the same rate in the system. So there's no net change in concentration. All right, so we usually think of the word equilibrium being associated with a root name equal. And it's important to understand that when we hear equilibrium, it doesn't represent equal concentrations. Okay? Each equilibrium has a preferred condition, whether it may be, some cases it may be equal amounts of products and reactants. It may favor the reactants greatly. It may favor the products greatly. Every system is unique at the point where that equilibrium is going to be reached. So the key thing is that it doesn't mean the concentration of the products and the reactants are equal to one another or the same. So what happens with some reactions, equilibria is going to be reached after almost all of the reactants have been consumed. So if that's the type of condition, we say that system favors the products. It went forward a long ways. All right, so if we think about the magnitudes of the arrows, it would have went forwards a long ways and reverse just a little bit. Okay, there's not very much reactants left. Everything's over here. R for reactants, P for products. Everything's here on the product side. Okay, and there's going to be other examples where you're going to have reactions where the reverse is true. So you're going to have systems where only a small percentage of the reactions occur, and they're consumed in the equilibrium, and the equilibrium favors that of the reactants in the system. So now if we looked at that type of a problem, it would be reactants and products, and the reactants are favored, and it's not going forward very much at all. Now, if I'm trying to make something in the lab, this is not what I want. because I'm going to start off with a lot of reactants and get very little product out of it. Back in Gen Chem 1, we used to talk about percent yield. Said percent yield, theoretical yield could be between 0 and 100%. If I'm trying to make a product, I want that yield to be as close to 100% as I can get it. So I would want to choose a system that equilibrium kinetics or equilibrium that favors that of the products, so I can get as far in that percent yield as I can in a system. All right. How do we know where it's at? And that's where the term called the equilibrium constant. So the equilibrium constant is a relationship between the products and reactants in a system. Okay, and we describe it, it's an expression of what's called the law of mass action. Okay, it's a relationship between the concentrations of both the products and reactants in the system for a given chemical reaction. So the way that we write it out is in the form of this. So we can assume I've got A is the subscripts represent the stoichiometric balance. So is it a 2, a 1, a 3? What does it mean to take the balance equation? I've got A plus B yields product C plus D. And if I look at the relationships that we have, we said the coefficients are the balancing terms. We always write this in terms of products over reactants. So the equilibrium constant is what we call K. It's unitless. It doesn't have units associated with it. But we take the molar concentrations for the products, we put those on top, and we raise it to the power of the stoichiometry. Okay, so the little c is going to be raised to the power concentration of C. The little d is going to go to the concentration of D. Now on the bottom, it's going to be the reactants, A to the little a power, B to the little b power. And almost every year a student makes this mistake. These are not added together, these are multiplied. All right, so we're multiplying these two things together, not adding them. Make sure we do that right. And this defines the relationship for a given system. And the key thing, this K is a constant at a given temperature. If I change the temperature, I can change it, but otherwise it's a constant. So what that means, if I change the concentration of one thing, so if I were to somehow decrease the concentration of C, now the value of K would change, so the system has to respond, and the equilibrium is going to have to shift in the forward or reverse direction, so that if C goes down, that means K would go down. To make it go back up, I would have to make the reaction run in the forward direction, and it's got to make some more C. And then these concentrations would go down if it goes forward a little bit, and this one would go up. So how far does it run C? Run in the forward direction to make more C. We can figure that out. All right, so how do we write these equilibrium constant expressions? So make sure we understand what the expression term means. The expression, the equilibrium constant is K. The equilibrium constant expression is this term. It's K equals products over reactants raised to the respective powers. So my posting or pasting here messed this up. So if I look at the reaction, 2 N2O5s decomposes to 4 N2Os and O2. The way I would write that K expression is products over reactants. So the products in the system, the products are the NO2. I'm going to put the NO2 in. Because of the 4 stoichiometry, I would put to the 4th power. Then the concentration of O2, and it's to the 1 power because it's the 1 stoichiometry, so we don't have to put anything there. That's the products. The reactants are the N2O5, dinitrogen pentoxide, and squared because of the 2 in front of it. And that's the law of mass balance for that particular reaction. This is called the equilibrium constant expression for that particular system. All right. Okay, so what does this value of K tell us, or what does it imply? If the K is much, much greater than 1, that means the reaction is favored. That means the reaction is favored towards the products, more so than the reactants. Okay, so products are going to be what will be the most predominant thing in that system when it's at equilibrium. Now, the opposite of this is going to be true. When K is much, much less than 1, that means the system's going to reach equilibrium when there are more reactant molecules present than products. So this system's going to favor the reactants. And if K is equal to 1, it means it's going to be pretty balanced between the two sides. Okay, it doesn't mean the concentrations are going to be exactly equal, because you can have things to these respective powers, and even if everything was at 1 molar, well, if you took 1 to any power, it's still 1, but if it were anything other than 1, when you raise it to a power, it may not be equal concentrations all the way around. And we'll look at examples of that in a second. So here's an example of something that has a large equilibrium constant in the forward direction. This is H2, hydrogen gas, plus Br2. Bromine gas yields 2 HBRs, hydrogen bromide. So if I put these things together in a reaction and are in a container, and they're all gases in the system, and seal it off, and just come back after some period of time, what I'd find is that most of the atoms that are there have combined to form the products, HBr. Okay, that's where most everything has went to. There's only a few things that are still the original reactants. So I've got just maybe a molecule of Br2 and a molecule of H2. Okay, so that tells me the fact that products are favored, that this is going to be a large number associated with it. If I looked at writing this expression, it's products raised to the power divided by the reactants raised to the power. In this case, they're both 1, so there's no power other than 1 associated with it. But that tells me something about the status of that reaction. Now, here's an example of something that's a small equilibrium constant. Okay, so how big can large be? Large could be 10. Right with the pen here. Large. It could be 10. It could be 100. It could be 10 to the 10th. Okay, 100 billion. It could be 10 to the 45th. Chemical reactions sometimes greatly favor products, especially in biological systems. And that if you see something that's that high of a K value, there's almost going to be no reactants left around to even see. Everything's going to go towards the products. So that's the type of systems that you get what you want out of the system. Sometimes they're small. So this is an example of where you have a system that's got a small value of K. So in the air, nitrogen and oxygen, the two most abundant gases in the air, 78% for nitrogen, 22% for oxygen roughly. Does some of it go forward to make NO, nitric oxide, and it combines at a 1 to 2 mole ratio. And the thing is, if I put those two gases in the air, very, very little amount goes forward and makes the products. And this is over-exaggerated. Almost all of the molecules that are present are those of the starting material, still there. So the fact that I find very few product molecules tells me this ratio of products raised to the power divided by reactants on the bottom raised to the respective power, that it's a small number, tells me I'm not going to find very many of the product molecules in that system. Okay, so what this tells us is that if the K is much, much greater than 1, the equilibrium lies to the right. In the forward direction, products are favored. If the K is much, much less than 1, it lies to the left, and the reactants are going to be favored in the system. Just something we can kind of see by looking at the numbers themselves. All right, now if we look at the relationship between K and the actual concentrations, we can start to rearrange these relationships to find out what the K values are for unknown systems. So whenever I take a reaction and if I write it backwards, what I do is I invert the equilibrium constant. It becomes 1 over K. So for a reaction written in the forward direction, A plus B yields C plus D. The K forward is products over reactants, raised to the respective powers of the stoichiometry. And if I were to reverse this reaction around, and now I wanted to think of it in the sense C plus D yields products A plus B, what would happen is now it would be products over reactants. A and B are now products. C and D are reactants. But the relationship between these two things is that K backwards equals to the inverse of K forwards. So anytime I spin a reaction around, go to the reverse one, it means that I need to inverse the value of K. Okay? And why this is going to be important, we're going to start rearranging all these different values to find new Ks that we don't know. We're going to take systems where I have a measured K, we're going to combine them to find Ks where I don't know the value of K. All right. So now if we look what happens when we multiply an equation together, what I do if I take the coefficients and I multiply it by some number, that means I raise the value of K by that factor. So if I looked at the reaction A plus B yields product C, the original K expression would be C to the C power divided by A to the A power and B to the B power. And now if I need to put these things together to make them balance out, I need 2 of everything in that reaction. So if it were 2 of everything in the reaction, so 2 little a's of A, 2 little b's of B, 2 little c's of C, now the expression is going to be C to the 2C power, A to the 2A power, B to the 2B power. So it's everything here. Now I'm just multiplying by itself again, so I'm squaring it. What happens, the K new is equal to the K original times whatever power you multiply that by, K to the n. All right, if it is 2 in this case, it would be everything multiplied by 2. So we can change the stoichiometries to fit what we need in systems. So being able to switch them around and then multiplying them by a factor, those are easy changes that we can do. Now what we do is when we add them together, when we add systems together to get a new equation, what we do is we take the product of the equilibrium constants from the old reactions. So if I take the 2 reactions, A decomposes to B, and B forms C. So if I took these 2 reactions and take it, the K1 for A would be products over reactants, B on top to the B power, A on bottom to the A power. And reaction 2, I don't know why that second 2 appeared there. Okay. Reaction 2 that's occurring is B yields C, so product C to the C power, product B, or reactant B to the B power, that's K2 for the system. So now if I want to take those 2 pieces of information and I want to combine these. So I'm going to take these 2 things and add them together. So I'm going to get a pen so I can do that. And I want to know for the reaction, little a yields little c, and I want to know what is the K value for this guy. So I could take these 2 pieces of information, little a to the A yields B to the B, and little b yields little c to the C. And if I add those 2 things together, I see what's common to both sides, it cancels out, or to alternating sides. So those 2 terms would cancel out left and right. So the net reaction I'd have is little a yields little c. So what I do now to find what is the new K value for this guy is I take the product, okay, of the old values of K. So where this was K1 and this was K2, capital K, K new is simply equal to the product of K1 times K2. And that K new is equal to products over reactants for the new system. The products are C to the C power. The reactants are A to the A power. So if I wanted to look at the individual terms, if I multiply these 2 things together, K1 times K2 What would happen if I multiply by K1 times K2? This representing K1, this representing K2. You'll see the A's and the B's cancel out. I'm left with C on top, little a on bottom. Okay? We can rearrange them. We can add them together. We can do whatever we want to. So while you want to do this, now let's put it to work. We learned some rules. I've got the reaction of two COF2s decomposes to CO2 plus CF4, and the K value is 2.2 times 10 to the 6. I want to know what the equilibrium constant would be for two CO2s plus two CF4s yield 4 COF2s. And that's going to be my K nu, if you want to think about it. All right, what's the relationship between the two things? It's the reverse. That's part of it, because what was a reactant on one side is now a product on the other side. So I know I'm going to need to spin it around, okay? So if I spin this guy around and invert it, it's going to be so from 1, I'm going to get CO2 plus CF4, and I'm dropping, they're all gas phase, so I'm not writing the gases in there. When you do the mastering chemistry, it's looking for the phases. I'll warn you that. So make sure you put the phases in the mastering chemistry. So if I were to spin this around, the K for this would be the inverse of 2.2 times 10 to the 6. Okay, but does that equal the system that I need? So are these two things equal to one another? What's the difference? What does it need?
Okay.
Needs another one of them. So what I need is, instead of just having one of these, I need to multiply everything by 2. So if I multiply everything by 2, 2, 2, this was a 2, you multiply it by 2, it's going to become 4. Now everything equals, so I need to take this and square it. Okay, so the K nu in this case would be equal to the inverse of 2.2 times 10 to the 6 squared. So it would be 2.1 times 10 to the minus 13 is what I got in my calculator.
So you just switch them, and look at it, compare it, and then the times it by whatever.
That's correct. Yeah. So if you can see that in your head to do it in one step, do it in one step. If you need to, write this out as, I'm going to go ahead and make it a line underneath here and write something different. So if you need to write it out this way, so this would be the inverse of K, and you took another one of them, and this is essentially what we're doing. We're adding two of these together. And this is the inverse of K. If I add those two things together, it would be 2. It would be 2. And these were already 2. Next, so this one was a 2. So 2 and 2 would make 4. So that would be the same as the one we're looking for now. 2, 2, 4. 2, 2, 4. And the K nu would be the product of 1 over the original K times 1 over the original K, which is the same as that squared, inverse of that squared. Okay. Question? All right, let's see where's next. It's not that, but that's coming. So what describes a system that's at equilibrium? Answer Answer it on your own. Nineteen of us here today. Couple more. Survey says, all right, most people think it's choice C, and that is correct. System that's at equilibriums where the forward and reverse rates are equal to 1. It's going to be no net change in the system. Okay? All right. You again. So I give you an equilibrium, 2A plus 3B yields C plus 2D. And I want to know which one of these is equal to K. Products over reactants. Okay, roll it. Predominantly the choice is A. Our choice is B. If we look at products over reactants, it's C over D, or C times D, and then the square because of the 2. And you put A squared, B cubed, and yeah, that's it. So if we look at the ones, let's look at why there's some of the other ones are not right. So what's wrong with A? They're inverted. It's products over reactants. What's wrong with C? So you multiplied the concentration to take them to the power. All right. And what's wrong with D at the bottom? It did the same thing, but it inverted them. Okay. All right. You're still going to get a chance to do some more of these. So we have to shift them a little bit, think about it slightly differently when we have gases. So when we have reactions that involve gases, how do we deal with the gas? So gases can be described with molar concentrations, but it's kind of hard to measure the molar concentration of a gas. What we do typically is we measure its pressure. And we know pressure is related to the concentration. So therefore we can take an equilibrium constant and we can express it in terms of ratios of partial pressures for a gas. So we take a system that all involves gases. Little a of A, little b of B yields products little c of C, little d of D. And the thing different is they're all now gases. Usually we think of things in solution. But for that, we can write, instead of writing concentrations, it's still true for the same as it is in solution, that it's related to the concentrations. K sub C means concentration base. K sub P is expressed in terms of pressures. It's the partial pressures of each one of those gases raised to its respective power. And it's still products over reactants raised to the power of whatever that stoichiometry is. Okay, so the partial pressure of C raised to the C power. Partial pressure of D raised to the D power. The reactants, partial pressure of A raised to the A power. Partial pressure of B raised to the B power. So we can write it either way. Now, sometimes K and P are equal to each other, and sometimes they're not. So when we're calculating K sub P is always described in terms of atmospheres. So, and when we dealt with some of the other ways that we've been dealing with things like the pressure and atmospheric pressure, we talked about torr or millimeters of mercury. Now we're going to have to convert everything into atmospheres to make this work in our calculations. So the relationship between K sub P and K sub C they're not necessarily the same because we have different units, but we have an equation that relates to two variables. K sub P is equal to K sub C times RT to the delta N power. And delta N is equal to the difference in the numbers of moles of reactants and products. So it's the summation, if we looked at our previous reaction, okay, where it was little a of A plus little b of B yields little c of C plus little d of D. If we had this reaction, delta N would be products minus reactants. It would be little c plus D minus little a plus little b. That's what delta N is. Now, in the cases where the number of moles are the same, there's no change in the number of moles. For the delta N is 0. If delta N is 0, this term becomes 0 in the system. So if this is 0, what's anything to the 0 power? 1. This term becomes 1. Therefore, K sub C equals K sub P. So whenever delta N is 0, it's going to be equal K sub C equals K sub P. So it could be that this were, could be 3A plus B yields 2C plus 2D. The fact that it's 4 and 4, 4 minus 4 is 0. The K sub C would equal K sub P in this case. Okay? That's the one you want. If it's not, you just have to deal with it. Okay? So if we look at the relationship we have between K sub C and K sub P and how we calculate that, I'm going to go over this derivation pretty quick. It's in the textbook. I'm not going to ask that you derive this. You can just, I want you to see where it's coming from. So if we think concentration, concentration is an expression of the number of moles per unit volume. Molar concentration is moles per, where A is the moles, or N sub A is the moles, and V is the volume of the gas in liters. And we can take the ideal gas law, PV equals nRT, and we can rearrange this, solving it for the pressure. So if I rearrange this for the pressure, isolate this variable, means I take the V down at the bottom. The partial pressure of A is equal to the number of moles divided by volume times RT. But we just said this ratio was equal to the concentration of A. So now I can just substitute in concentration of A. So that means the partial pressure of A is equal to the concentration of A times RT in the system. So now if I rearrange this for what is the concentration of A, it's the partial pressure divided by RT. So I've rearranged it to that point. Now that I know what it is for a single species in a system, I can just say for any gas, X, and I can substitute that into my K expression, where K sub C is products over reactants raised to the respective powers of the stoichiometries. And now I can make that substitution and say K sub C for a gas, or instead of saying the concentration of that gas, I'm going to put the partial pressure of the gas times R divided by RT. So instead of concentration of C, I'm putting the partial pressure divided by RT raised to the C power. Same for the concentration of D, partial pressure of D divided by RT to the little d power. On the bottom, the reactants, concentration of A, I'm substituting in partial pressure of A divided by RT to the A power. For B on the bottom, concentration of B, I'm putting partial pressure of B divided by RT raised to the little b. So now look at the things that are common that I can factor out. What I can factor out are all these partial pressures. Okay? So this ratio of the partial pressures is the definition of what we said Kp was on the previous page. So everything inside the parentheses here equals Kp. And then on the bottom, what I have are the right-hand side of the equation. What we have is that it's the inverse of RT raised to the CD power divided by the inverse of RT raised to the AV power. So if I put those two things together, it's the inverse of RT raised to the power of C plus D, and this is hard to see the minus, at least up close it is for me, minus the summation of little a plus b. So now when you rearrange that, this is where it comes to down the bottom. So if you put all this stuff together, Kc RT raised to the power of the difference in the number of moles. I just want you to see where it's come from. Only thing I care about is we apply it. So let's look at an application. All right, so the equilibrium concentration for carbon monoxide with molecular chlorine. So I've got carbon monoxide and molecular chlorine to form the products COCl2. So this is my product. It gives me the temperature, 74 Celsius, and it tells me what the concentrations are of all the species. So it tells me what's the concentration of the carbon monoxide, the concentration of the molecular chlorine, and the product, the COCl2. So I know all of those molar concentrations. So if I want to find out what K sub C is, it wants to know what is K sub C and what is K sub P. K sub C is products over reactants. So it's the concentration of the COCl2 divided by the concentration of the CO and the concentration of the CO2. Everything's to the one stoichiometry, so nothing's raised to a higher power. Okay, so all I have to do is plug in those various concentrations. So for the concentration of the COCl2, I just need to put in its concentration. I've got that number. The concentration of the carbon monoxide, I go find its concentration, 0.012. I've got that one. And then finally, the concentration of the molecular chlorine, that's given. I plug in that concentration, and now it's just multiplying and dividing. I find out K sub C is 220. Now what I want to do is take the relationship to find out what is K sub P. So now I'm going to take the equation that we had on the previous page that we derived, and K sub P is equal to K sub C times RT to the delta N. Now in this case, delta N is a minus 1. So summation of the products is 1, summations of the reactants is 2. 1 minus 2 is a negative 1. So delta N is a minus 1. The value of R is the R that we used, and we throw every R at you. R in chapter 13 or chapter 14 was 8.314. Now we're back to the gas constant R from ideal gas law. It's R is 0.0821. If we take our temperature, we got to get the temperature in Kelvin. So 74 Celsius, convert it to Kelvin at 273. It's 347. So now if I rearrange this to find out what, or plug in the numbers for K sub C, it's 220. I've got R and T raised to the negative 1 power. I find out that K sub P value is 7.7. Not tricky algebra. It's just a matter of just cranking things through, plugging in. You're going to have to figure out what equation to use and just throw the numbers into it. Recognize what R to use and make sure you get the temperature in Kelvin. Yes?
So will the questions always have, like, how it says CO equals 12.012? Will it always, like, give us like that? We just have to fill in the...
Nope.
Okay.
Let's look at it. Another example. Okay, sometimes we're going to take and be given pressures. So the thing that critical thinking aspect that I want you to think about, I'm going to go back on this guy, is if I think about this system, any of these could be variables I could ask you for, including K sub P. So, or even temperature in this system. So the variables could be any of these guys, or temperature. Okay? So I'm going to hit you for one of them. It's not like I promise you, it's going to be one of them. Okay? The key thing is to recognize this is a system where I need to relate a gas to the concentration. And this is the equation that we use for that. It's recognizing that. And then you just crank through it. All right, here's a different example. So this one, I know what K sub P is. K sub P is 158 at 1,000 degrees. And it tells me my reaction, two NO2s, you'll have 2 NOs plus O2. And I want to know what is the equilibrium pressure of O2 if the concentration of the N2O is 0.4 and the concentration of the NO is 0.27. So what I'm looking for is what is the partial pressure of the O2. So in this case, I'm just dealing with, I don't have to solve concentration based. I just have to recognize now I'm using the ratio of the partial pressures. And what are the things that I know? I know K sub P, it's 158. So that's given. All right. I know the concentration of the partial pressure of the NO2. So the that 2 should be down here. I messed some of those up. It's that concentration squared on the bottom, so I know that term. Why is it squared? Because the 2 here. And then on the product side, the concentration of the NO squared, I know it's given in this. So I know this term. So this is the only thing that I don't know. It's just a simple matter of rearrangement. So I'm looking for PO2. So if I'm going to rearrange this equation, I choose to rearrange the algebra before I plug numbers in. So I'm going to cross multiply and take this term up here. So it's going to go on top. All right. I'm going to cross divide. This term is going to go over the bottom and be down here. So when I rearrange, PO2 is equal to K sub P times the PNO2 squared because of the 2 term divided by the concentration of the NO squared because of the 2 term. So now it's just cranking through, plugging numbers in. Kp times the concentration of P, or the partial pressure of NO2 squared. NO2 squared, that was given to me. NO2 squared. And then, or NO2, I still have to square it. Then the concentration of the NO is 0.27. That's divided, so it's down on the bottom. I got to square it as well. Takes a lot of pressure to make that happen. Okay, 347 atmospheres. That's 350 times atmospheric pressure. We would collapse instantly under that type of pressure. But in chemical reactions, this is inside some type of a reactor because it's running at 1,000 degrees. It's 1,200 degrees Celsius. It's hot. Okay? We do reactions like that all the time in systems. Big 3-inch steel containers. Okay? Thick walls, high temperature, high pressure to drive a reaction in the direction we need to go. All right? What's next? That was y'all's. That's wrong. Okay, let's see if we can get that one right.
Is it group?
Sure, make it a group question.
Okay. That's your color.
Anybody want to take a guess?
I'm actually still.
Okay. I'd rather you try to work it out. Maybe you don't see what I see.
Okay, so
You do, because all 19 of you answered it already. So let's work through it. Since,
wait, no, you haven't.
Oh.
You haven't opened it up yet.
never mind. Now 19 of you answered.
You're not be like, chill.
Now go.
Isn't it just CD?
don't know, I did this, and I got A. I did that, and I got A. Would you look You know, you're a very smart lady because I'm fine, yeah. What do you get when you do that? Don't look at that one. That one's wrong.
Just need some answers.
See? I'm so done. D.
That's one. Man coded. That could have been a setup. I could have accidentally shown you the mark. That mark, well, that would be wrong if that's not really the answer hidden underneath there. Let's see how to work it. Maybe you didn't see that. Okay, most of you put D, that's good. So if we look at our equation, we need to know what delta N is. So I've got products are 4, reactants are 2. So delta N is products minus reactants, which is 2. Okay, so I want to know what K sub P is. So I'm just going to plug everything directly in my equation. K sub P is equal to K sub C. No, I'm looking for K sub C. So this is my unknown, so I got to rearrange for that. So K sub C is equal to K sub P divided by RT raised to the delta N power. So Kp is 7.7 times 10 to the 24th. RT is 0.0821 times the temperature is 298, and then raised to the power of positive 2. And if I multiply that out, I do get 1.29 times 10 to the 22nd. Okay. I'll try not to do that to you again. That takes the fun out of problem. Okay, question on that. Make sure you and your calculator like each other enough so that you can get that answer out of that calculation. Okay? All right. We're going to continue on, we're on slide 33 going forward, so homogeneous equilibria. That's where we'll start come Wednesday. Wednesday, what's going on Wednesday?
No school. Will not be here.
Oh no, classes start at 1. Yeah, but we're out at 1, so. But afternoon labs meet. We won't do anything, but afternoon labs meet on Wednesday. Okay. Wait at like 30. Find out who else. Try to get us. Maybe try to schedule one more.
Okay.
Okay. Wake up tomorrow. Okay. So there's several students that are going to be making it up. Go down and talk to John. I don't know what the date is. Do you know what date y'all are doing making the layup yet?
No, we have to email.
Okay. Y'all all need to talk to John and find out. We need to try to do it in one effort. We're making it. All right. So there's like 6 of y'all that have to do it.